All right, welcome. Today we are going to build our very own geometric toolkit. We're going to dig into the principles of balance and precision that designers and engineers use to create, well, pretty much everything, from huge bridges to tiny little circuits.
I mean, just look at this thing. When you see a structure like this, its strength, its stability, it all comes down to perfect symmetry, to finding the absolute dead center of every single component. And that's true whether you're building a massive bridge or designing a microscopic computer chip. Balance is key.
So how do they actually pull that off? Is it just guesswork? No way. They use these fundamental geometric principles, and today we're going to master two of the most important tools in that whole process.
Okay, so here's our game plan. We'll start with the basic idea of balance in geometry. Then we'll introduce our two new tools, the perpendicular bisector and the angle bisector. After that, the fun really starts. We'll use them to solve some puzzles, and then we'll even write the equation for perfect balance. Let's get into it.
Okay, first things first. Before we can really use our tools, we gotta get a handle on one key idea that makes everything else work. It's what it means to be perfectly balanced, or in the language of geometry, equidistant.
It sounds fancy, but it's actually super simple. It just means being the exact same distance away from two different things. That's it. And believe it or not, this one little concept is the secret sauce for our entire toolkit today.
All right, let's meet our first tool. This one is the ultimate line splitter. It's designed to solve a really common problem. How do you find the absolute perfect center of any straight line? Well, you use the perpendicular bisector.
And the name pretty much tells you everything you need to know. First, perpendicular. That means it hits the line at a perfect 90-degree angle. See that little square symbol? That's your clue. Then, bisector. That just means it chops the segment into two perfectly equal halves, right at its midpoint.
And here's where the magic really happens. This whole thing is a two-way street. The theorem on the left says if a point is on that perpendicular bisector, then it's guaranteed to be the same distance from both endpoints. The converse on the right just flips it around. It says if a point is the same distance from both endpoints, then it absolutely has to be on the perpendicular bisector. It works both ways, which is what makes it so useful.
Okay, on to tool number 2 in our kit. This one tackles a similar problem, but instead of splitting a line, it's all about perfectly splitting a corner, or an angle.
Now, it's super important to know when to use which tool. The perpendicular bisector, that's for line segments. It finds points that are the same distance from the end points. But the angle bisector is for, you guessed it, angles. It finds points that are the same distance from the sides of the angle. Ends versus sides, that's the big difference.
And check it out, we see that same beautiful two-way logic. The theorem says, if a point is on the angle bisector, then it's equidistant from the two sides, and the converse flips it. If a point is equidistant from the sides, then it must be on the angle bisector. See? It's a perfect relationship that works in both directions.
Okay, enough theory. We've got our tools, we've read the instruction manual. Let's open up the workshop and actually solve some stuff. Time to put these tools to the test.
First puzzle up. So what are we looking at here? I see a right angle symbol, and those little tick marks, they're telling me the line segment is split right down the middle. That's our flashing sign that we've got a perpendicular bisector. So the theorem says any point on that line, like point S, has to be the same distance from P and R. So if PS is 6.8, RS has to be 6.8. Done! Now for this one, we're going to work backwards. We're using the converse. The diagram tells us that EH and GH are both 24. Since point H is equidistant from E and G, our converse theorem kicks in and tells us that HF must be a perpendicular bisector. And since it's a bisector, it has to split EG in half. So if the one half, FG, is 9.5, the whole thing is just double that, 19. And of course, we can throw some algebra in here, why not? The diagram shows us all the signs of a perpendicular bisector. That's our cue. We know it means AD has to be equal to CD. So we just set up an equation. 5x equals 3x plus 14. A little algebra, subtract 3x from both sides, you get 2x equals 14. So x equals 7. But wait, we're not done. The question wants the length of AD, so we plug 7 back into 5x, and we get 35. Okay, this next one, this is a classic. You gotta look really, really close at this train bridge. Do we have enough information to say for sure that that vertical support is a perpendicular bisector? What's missing here?
And the answer is no. And this is super important. We know the support bisects the track,
because those little tick marks tell us KL and ML are equal. But we have no idea if it's perpendicular. There's no little square symbol telling us it's a 90-degree angle. You absolutely need both conditions, a midpoint and a right angle, to use the theorem.
Okay, let's take this out of the textbook and onto the soccer field. Check this out. A goalie is standing in just the right spot so that the angle from the ball to the left goalpost is exactly the same as the angle to the right goalpost. So the question is, does the goalie have to move farther to block a shot to the left or to the right?
Well, because those angles are the same, we know for a fact the goalie is standing right on the angle bisector. And what does our theorem tell us? It says any point on that line is the same distance from the sides of the angle, which, in this case, are the paths of the two shots. So the goalie has to move the exact same distance. Pretty cool, right? That's geometry giving you a real-world competitive edge.
All right, for our final challenge, we're going to level up big time. We're going from just using these rules to actually writing them in the universal language of math, an algebraic equation. To write the equation for a perpendicular bisector, it's actually just a straightforward four-step recipe. Step 1, find the midpoint of your line segment. You just average the coordinates. Step 2, find the slope of that original line. Rise over run. Step 3, get the perpendicular slope. This is the easy part. You just flip the fraction and switch the sign. And finally, step 4, you plug that new slope and your midpoint into the equation for a line.
So for our segment PQ, we do the math. The midpoint is 1, 2. The original slope is -1/3. So our perpendicular slope is the negative reciprocal, which is +3. We plug all that in and boom, y equals 3x minus 1. And just like that, you have the perfect algebraic formula for that line of balance.
So let's do a quick recap of what's in our new toolkit. We've got perpendicular bisectors, which are all about the endpoints of a line. We've got angle bisectors for the sides of an angle. We know these powerful rules work in both directions, and we can even translate them into precise algebraic equations. You see, this isn't just about lines and angles on a page. This is a fundamental principle of design, of engineering, even of sports strategy. It's how you build a stable bridge or find the perfect position on the field. So the real question is, now that you know how to find and create perfect balance, what will you design?